Hi there, this is Sean Alexander with Alexander Tutoring, and today's lesson is what is the derivative? This is a subject that I've noticed causes a lot of calculus students a lot of grief, in that they don't really get what the derivative is as they move through the calculus class, and that causes a lot of conceptual misunderstandings. They can learn how to take the derivative like mechanically, going through the motions, but they don't really get what it means. And here at AT, we are all about knowing the meaning behind everything we do. So I want to talk about this for a little bit because I think it's going to make your calculus class go way smoother if you just get this concept here. So the derivative is the slope of the tangent line. If I ask you what the slope of this function in pink here is, what's the slope of this function? You should take pause because that's kind of a silly question because you got to say, well, where? For example, if I want to know the slope here, we've got to look at what's called the slope of the tangent line, or a line that just touches the function at one point. And you can see that the slope at that location, at that x value, takes on one value. You can see it's uphill, so it's a positive slope. But if we looked at another location, say over here, corresponding to a different x value, well, now look, the tangent line is now downhill, going from left to right, and so it has a negative slope. So we can see that the slope of the tangent line is different at these different locations. So basically, the slope of this function f of x is different everywhere. Okay? So the next question is, well, how do we find this tangent line? And it turns out that this is a fascinating question that stumped mathematicians for thousands of years, and we have Newton or possibly Leibniz around the same time to thank for figuring out this problem. So I really want to show you what the problem is and how we solve it. So if we use traditional slope methods from your Algebra 1 class, do you guys remember this good old y2 minus y1 over x2 minus x1? I hope you know that one, otherwise you're in the wrong class. The thing about this formula for finding slope is that it requires 2 points to make the calculation. So to prove a point, I'm going to just pick 2 random points on our function. Let's say this one and this one. And I'm going to try and calculate the slope. So this point here, I'm going to relabel my x values here, so let's get rid of these guys. Okay, so we'll call this x1 again. And the second point, x2. And those correspond to y values. So if we go shoot straight over to the y-axis, we'll have y1. And for this guy, y2. Okay? That means our first point has coordinates x1, y1, and our second point has coordinates x2, y2. The 1s and 2s are just so you don't confuse the 2 points. Okay, so let's just run this thing through our formula and see what happens. Basically, it's just as is. So if we pass these points through our standard slope formula, what we're going to end up calculating is the slope of the following line, or the slope of the line that goes through those 2 points. Okay? We just calculated the slope of that line. So what's wrong with that? Well, it's not quite right. So we're trying to get the slope of the tangent line, and you can see maybe it's an approximation of the tangent line in a certain region, but it's not exact. So the next thing you would think to do, which would make sense, is let's pull those points in closer together, right, to get a more accurate representation of the slope at a point. So let's draw it again. Same pink function. And let's try to squeeze those points together. So I'm going to keep this first one right about where it was, and now I'm going to make the second one really close. Okay? So this is our new x1, y1, 2, excuse me, x2, sorry. And this one is y1, y2. Okay, so you can see now that if we calculate the slope of that line using the standard formula, well, we're going to get the slope of this line. And is that the right answer? Well, it's a lot closer, right? You can argue that basically we took x2 closer to x1. And so you can see that it's a lot closer to the slope of the tangent line, but it's still not perfect, right? It's still not right on that f of x pink line. So of course you say, all right, well, let's get those things as close as possible, those 2 points, but something happens, we can't just pull them right on top of each other because then something bad happens. What happens if you pull them right on top of each other? I'll give you a second to think about that while I draw the next graph. Well, if you do that, let's see what happens when we calculate the slope formula. We're going to get, if the 2 points are the same point, then x1 equals x2 and y1 equals y2, right? 2 points on the same point. Now what happens when we do our slope formula? We have a little bit of a problem. We get y1 minus y1, because remember y2 and y1 are the same now, over x1 minus x1 equals 0 over 0. That's not good. 0 over 0 is, of course, undefined, which is not a great answer for the slope of the tangent line. I mean, we can draw the thing. It should have a value that's not undefined, right? So we clearly have a problem here. So let's see how the genius of Newton, or Leibniz, he's the other guy who figured out calculus, approached this problem. So we're just going to do a very clever trick, and we're just going to relabel stuff. Okay, so remember before we called point 1 x1, we called point 2. Now, the only little change I'm going to do here, instead of calling this guy y1, I'm going to call it f of x1, which is totally legit, because if I plug x1 into the function f of x, the pink line, I should get f of x1, which is the y value, corresponding y value. Similarly, I can call, instead of y2, I can use f of x2. Why? Because when you plug x2 into the function, out pops the corresponding y value, y2. Okay, so now if we plug that into our standard slope formula, what do we get? We get of y2, we're going to put okay, all I did was replace y2 minus y1 with f of x2 minus f of x1. Furthermore, instead of x2 and x1, I'm going to call the distance between x1 and x2 h. Because what are we trying to do? We're trying to get x1 and x2 like right on top of each other, right? So if we do that, would you agree that x2 minus x1 equals h? Why? Well, that's pretty obvious, right? This distance minus this distance is the distance in between, or h. Okay, or we could say, just rearranging it here. Okay, so going back to our slope formula, again, all I've really done is relabel things. And I'm going to write, instead of x2 minus x1, I'm going to write h, because that's what we defined it as. Okay, so this is just clever relabeling. Furthermore, for this x2 right here, I'm going to plug this guy in, right? Because x2 is h plus x1, so then we get okay? And what we basically want to do is squeeze h down to 0, right? H is the distance between the 2 points. But our problem was getting that when we made them the same point, we got 0 over 0. So what we really want to do is squeeze h down to 0. And what we call that is the limit. So in the limit, as h goes to 0, that means we squeeze down to 0. H we can't make 0 because we get that undefined result. But what if we made h like 0.0000, like a million zeros, 1? We could do that, right? And that would give us a super, super close answer to the slope of the tangent line. So the idea is, as h gets smaller and smaller, we squeeze it down to almost nothing, we get closer and closer and closer to the right answer for the slope. And so if we put this limit thing here, that means we want h to get like as close to 0 as humanly freaking possible. I'm leaving the little ones off my x's because they're all the same now, we don't really need it. Okay, and we arrive at the definition of the derivative. Now what's fascinating about this is we didn't really do anything other than relabel stuff, right? We called, instead of y1, y2, we used f of x1, f of x2. Instead of x2 minus x1, we use h, but it's really all the same thing. So we haven't really I mean, so this is actually a profound result. We can't really see why yet, though, right? Like, okay, who cares? Why don't we get, if h is 0, we still get it divided by 0. What's the deal? So I think it's best to understand how the power of this by using a quick, simple example. So I haven't given you a function yet. All I've said is f of x. Now I'm going to give you an actual function that you're probably familiar with. X squared. We've all seen it. Okay. So now we're going to run x squared through our new slope formula in the box here. So, and let's see what happens. So we say the slope of the tangent line is equal to the limit as h goes to 0. F of x plus h. Okay, so what does this guy say? This says plug h plus x into the function, right? So now our function is x squared. So if I plug h plus x into the function, what do I get? I get that, right? I just plug h plus x in for x. Okay, and then we subtract off f of x, which is just the original function, in this case, x squared, all divided by h. Okay, still, if we make h 0, we're still divided by 0, no bueno. But let's keep working on this a little bit and see what happens. I'm going to square or FOIL out this term here, that first term. So what do we get? I'll assume you know how to do this. If you don't, you're in the wrong class. Okay, and then we can simplify the top. You'll notice that the x squareds go away. Look at that. And look what's left. We have h squared plus 2xh. There's an h common to both terms, so I'm going to factor that out. And here it comes, folks, the big magic moment of calculus, the thing that took thousands of years to figure out, that no one could figure out. Remember that problem? If we plug a 0 in for h, we divide by 0. Boom. H cancels out. There's no more h's in the denominator. And that is the key, the trick to the derivative. You got to get that h to cancel out in the denominator so you don't divide by 0. Check this out. Now we can just straight up set h to 0 without dividing by 0. So we're just going to plug a 0 in for h, and we get that the slope of the tangent line is 2x. What does that even mean? Well, remember I said the slope's different everywhere? This is super awesome because now we can determine the slope of the tangent line at any x value we want. All we got to do is plug it in. So for example, I'll just give you a little visual here to go along with it. So what's x squared looks like? It's our parabola. What does this formula say? At the location, x is 0. So if we plug a 0 in right here, what do we get? The slope is 0. Is that true? Well, here's x is 0. What's the slope of the tangent line? You can see it's a flat line, so the slope is 0. It works. What if x was equal to 1? Well, then we get 2 times 1 is 2. And I'm not using the squares here. I'll just say that's 1 right here. The slope of the tangent line would be 1. What if it was negative 1 was the x value? Then we'd be over here. Our equation predicts the slope should be negative 2. And check it out. It is negative 2, downhill. So this allows us to figure out the slope of the tangent line wherever we want. So that is what the derivative is. It is the slope of the tangent line, and the way you figure it out, the big magic of calculus, is you got to get that h to cancel in the denominator so you're not dividing by 0. Okay, guys, I hope you find this helpful. Take care. Bye.